before I start. Any questions, concerns, or comments? No? You ready for some math? So last week on our worksheet on the backside, we were looking at the set, Zn star. So this is, remember this stuff? So this is the numbers, the integers 1, 2, up through n minus 1. So it's like the non-zero Zn guys. And if you have this under multiplication, this forms a group if and only if n is prime. Okay, so again, let me just emphasize what this notation means, right? This is just the set 1, Zn is the set 0, 1, 2, up through n minus 1, but this means non-zero, so this is up through n minus 1. So there's n minus 1 elements, right? And it's considered under multiplication, modulo n. Right? And this is a group if and only if n is prime. So just maybe some examples. Z5. This is 1, 2, 3, 4. This is a group under multiplication. Okay, so remember, group means you have an identity. Of course, that's the 1 under multiplication. And you've got inverses. So in this setting, everything has an inverse. For instance, 2 times 3 is 1, modulo 5. So the inverse of 2 would be 3, and the inverse of 3 is 2. 2 inverse is 3. Okay, so I think you guys are familiar with this stuff. I just want to, again, let's prove this. Okay, so on your worksheet, I wanted to, one direction of this, right? We wanted to show that if n was composite, then you actually don't have a group. Okay, so let's prove this guy. So I guess what I'm going to prove here is actually this direction. And it's sort of in a contrapositive. So what I want to do is assume that n can be factored as, say, a times b. So just now as an integer, right? This is regular old multiplication. And, let's assume that it's actually composite, where, so what does it mean to be a composite number? That means I can write it as, a times b, where a is not 1 and not n, right? So I mean, to say you're a composite number means that I can write n as something smaller than n times something smaller, right? So I mean, it's a composite number. Then we claim that a has no inverse in this setting. So this is under multiplication, right? So again, this was on your worksheet, so maybe you guys did think about this, but I just want to go through the argument. Okay, well, let's see. If we had a times something, star something equals 1, so if we had an inverse of a, and what does that actually mean, right? So it means that when I multiply a times this x thing, I get 1 mod 5, right? That's what this means to say you're 1. So i.e., so this is if and only if, I can put it this way, right? We have, this guy equals 1 if and only if a times x is equivalent to 1 mod n, right? And that's what it means to say a times x is 1. It means that ax is equivalent to 1 mod n. And what does it mean to say that you're equivalent to 1 mod n? It means that you're equal to 1 plus some multiple of n, right? This is the usual, okay? So, I don't know, qn or something, some multiple of n. Okay? Well, now we're going to use the fact that n is ab. So let's pull this down here. That means that ax is equal to 1 plus q times ab, right? Which implies, if I put all my a stuff on one side, this is telling me that a times x minus qb equals 1, right? So just collecting all my a's on one side, you see that? Now what's the problem? I mean, what's the, these are all integers here. Everything in sight is an integer. You've got an integer times an integer is 1. So what does that mean a has to be? I mean, there's two choices, right? integer times something, integer is 1, so what does a have to be? Or minus 1. I mean, these are just integers now, we're just looking at, right? These are just straight up integers. If I have integer times an integer is 1, it can't be 5 times an integer is 1, right? It has to be 1 or minus 1. And that means that's a contradiction. I mean, that's a... So in fact, n could not be factored as a... n is not composite. You guys see that? So again, this shouldn't be too shocked. Right? This is just an integer times an integer is 1. Therefore, both of these guys are 1 or minus 1. Right? You can't multiply an integer times something and get 1 unless you are 1 or minus 1. Okay, so if you had so this is sort of the contrapositive of this left to right statement. The only way that you can get a group is if you are prime. Now, we haven't proved that if you're prime, you actually are a group. That's the next step. Right? Let's prove this direction. Suppose n is prime now. We're going to prove that, that this thing's a group. Okay? Now, I mean, to prove that something's a group, you have to go through all the associativity units, right? So associativity, I'm going to be a little bit lazy. We know it's associated because this is multiplication just restricted to modulo n, and I'm going to be a little bit hand-wavy here and just say, well, it's associated because usual multiplication is associated. We're just restricting modulo n. What I really need to check is for inverses, right? So I mean, I should say that we have a unit, an identity. Sorry, right? An identity. What is the identity? Given by 1, right? Is that clear? I mean, we actually had that in any case, right? We always had this one guy. So the thing we have to check here is, do we have inverses? It remains to check. Remains to see that every element, each x in Zn star, has an inverse, i.e., an element y in Zn star, well, such that, usual story, x, y equals 1, and now this is all happening in modulo n, right? So this is the... Okay, well, I don't know if you guys thought about this one at all. So, so we're going to use that kind of common trick we've used before in this class. If n is prime, what is the GCD of n and this element x that you gave me, right? So let's let x be in the. So let's let x be one of these guys, non-zero. Right, a non-zero number between 1 and n minus 1. N now is assumed to be prime. So what's the GCD of n and x? 1, right? Because x is a number smaller than n, and n is prime. There's no divisors of n. So since n is prime, we have GCD of x and n is 1. Just as numbers now. I mean, these, So I'm always going back and forth between sort of Zn star and then thinking of it as a usual integer. But you guys hopefully see what I'm doing. Okay, so what's the usual story when I don't know if when you guys took elementary number theory? I think we've done it before, right? It was on your first homework as well. If I have two numbers that have a GCD of anything, I can write that GCD as an integer combination, right? This is this usual, I forgot the name of this theorem, right? So we can write, you guys remember this from your, what's the name of this thing?
The division algorithm.
It's not the division algorithm, right? It's, well, the Euclidean algorithm is getting the GCD, but this is attributed to some other, do you know the name? Or?
It's like Bayes' theorem, like
Bayes?
It's like
Yeah, it's Bayes'.
Oh, Bayes? Okay, not Bayes, not the Barbalus, but okay. Well, it's got some name attributed. That's how you know it's important. But yeah, I mean, Euclidean algorithm is giving the GCD via this kind of algorithm. But the fact that you can write one, I think it's something like that. I forgot. you can write 1 as something x plus something n, right, where a and b are integers. Right, you can write the GCD as an integer combination of the x and n. Okay, and you see now we're in good shape because, well, let's collect, this implies that 1 minus bn is equal to ax. Okay? Well, what's that saying? It's saying that ax is equal to 1 plus a multiple of n. Right? This is telling you that ax is equivalent to 1 mod n. And that's exactly what we wanted, right? There's our inverse. So I should have called it y maybe, but that's my inverse there. So a is equal to x inverse. Right? And that's what it means to be an inverse, is that when you multiply it, you get 1 mod n. Okay, so anytime you have a prime here, you get a set of one less number of elements, and it's a group, which is nice. It's kind of a nice fact. It's used in a lot of kind of even modern cryptography and things like this. We'll come back to this guy. So questions about this sort of proof of this important fact? The natural question, at least I hope it was on your worksheet, what kind of group is this? Well, it's clearly abelian, right? Because this is just multiplication, which is an abelian thing. So it should be clear that these groups are always abelian. Okay, so let me just conclude. So we know ZP, I'll call it now, ZP star dot is a group. Okay, and this is where P is a prime. Okay, so it's a group of P minus 1 elements, right? So maybe with P minus 1 elements. And again, it's clearly abelian, so it's easy to see ZP star is abelian just because it's multiplication. I mean, again, multiplication of usual integers is commutative, so this is just inheriting that. But the question is it actually a cyclic group, right, which is stronger? Cyclic groups are always abelian, but it's a stronger condition. So is ZP star cyclic? Okay, so you guys remember, cyclic groups are a special case of abelian, right? So in your world of groups, you've got the sort of abelian groups are here maybe. And you've got the cyclic groups live in here. But there's examples of abelian groups that are not cyclic, like Z2 cross Z2. That'd be a nice thing to just have. And of course, there's many groups that are not abelian, like the symmetric group S3 is not abelian. So hopefully this picture is kind of somewhere in the back of your head. So we want to know, do these ZP star things actually sit in the sort of smallest case, the smallest subset? Well, let's see. So for this guy, I think we might have talked about this, right? For Z5. I mean, how do you show that something's cyclic? The brute force way is to just find a generator. And that's always going to work, right? If it is a generator, then you can find it. There's 4 things to check. And of course, I shouldn't check the identity as a generator because powers of the identity are not going to be very interesting. So in the case of Z5 star, we want to find a generator. So what do you guys want to try? 2? Okay, let's consider the subgroup generated by 2, right? So we know that's going to be a subgroup. The question is it the whole thing? Well, what does it consist of? So it's 2, which is 2 to the first power. What's 2 squared? Well, here it's literally 2 times 2, right? This time we're actually using multiplication. So what is 2 squared? Okay. What is 2 cubed? That's 8, which is 3 mod 5. 2 to the 4th? 1. So it looks like we're good. Right, that's the identity. We got all of them as a power of 2. Okay, so yes, it's cyclic. Right? I mean, that's how you prove it. This is implying that Z5 star is cyclic. I know, let's do one more. What about Z7?
What's on the homework?
That was on the homework as,
Well,
How was
if
it
you use
phrased?
the trick, we were proving these were isomorphic to each other. And we use G7.
oh, and that, okay, that was on the homework, okay. Well, what I'm trying to get at here, there's a big theorem that we're actually gonna prove later in class. We actually need more machinery to, yeah, I don't know how much I should say. So you know that Z7 is cyclic?
Yeah.
That's true. So, okay, good, I can appeal to the homework now. But I wanted to get but I wanted to show you that you don't always get lucky, right? It is cyclic, but I think 2 is not gonna work, right? So in this case, what is 2? So the subgroup generated by 2 consists of 2 squared, and then 2 cubed, which is 1, and that's it, right? Because now, so this is 2 squared, 2 cubed. So this is not a generator, right? It's a proper subgroup. But, of course, there is a generator. I guess 3 might work. But 3, does 3 work? Let's see. So this consists of 3. What's 3 squared? Which is 2. That's 3 squared. What's 3 cubed? This times 3, which is 3 to the 4th is 4. 3 to the 5th is this thing times 3, which is 5. 3 to the 6th is this thing times 3, which is 1. And that's the whole thing, right? 1, 2, 3, 4, 5, 6. Okay, so again, it's cyclic. Okay, so the conclusion is that Z7 is cyclic. Okay, well the reason I'm going through all this kind of maybe tedious calculation is that the answer to this question is yes. Okay, they're always cyclic. But there's no known algorithm that's better than what I've been doing. So there's no algorithm other than just brute force looking for generators that finds a generator. And that's actually, again, that's not so much anymore these days, but for a while that was actually used in some cryptography algorithms, that if you have a very large P here, you know that that's a cyclic group, and you know there's a generator out there. But there's no quick algorithm to actually find it. You know, the algorithm that I'm running is the best known, which is very silly, right? I'm just checking everything. I'm just going through the list. So the answer is yes, and we'll prove this later. It's actually not easy to prove. I mean, somehow you need a little bit more machinery to kind of... We'll prove something more general later. And like I said, the kind of interesting thing, I think, is that there is no known algorithm. I should say known algorithm to find a generator that's better than just brute force. I mean, there is a generator out there, so you can just test. It's a finite thing, right? So you can just go through the whole list. You know, so aside from just brute force, I'll just put this in quotes. I'm not going to make this precise, but you know, just listing all of them and checking, right? I mean, maybe that doesn't look so special when you're looking at just 7 things, or 6 things, I guess. But you know, you can imagine if the prime has 1,000 digits, and you have to check all these guys that takes a while, right? So that would be an expensive thing to check. Okay, so that's, again, more than I wanted to say, but now you guys know something about ZP. We're going to come back to that guy. Questions about ZP? And so they're all cyclic, they all sit in here. But they kind of have mysterious generators. I mean, you don't really know what they are until you actually go and calculate things. Okay, so today, let's see, I want to push on. Let's see, I think we pretty much finished our equivalence classes, right? So I think I'll just cut to the new stuff. So today we're actually going to prove our first theorem, or at least get most of the way to it, to stating it. I would say our first kind of real theorem of group theory. So this is from chapter 13. So these are called cosets. This is going to be a new definition of things. And let me just say the kind of motivation here is, given a group G, okay, so we're changing gears, right? Now we're looking at not these guys anymore, but any group. What do the subgroups look like? And, well, so that's a vague question. In particular, what we're going to look at today is how many elements do they have? So we're usually going to look at a finite group because somehow that's where this theory really has most to say, but it's a general statement. So, it's about all groups. We're mostly going to be looking at finite groups. How many elements can a subgroup have? So, we should say, so if I give you a group G, it always comes for free with two subgroups, right? So let me just write that down so we can get that out of the way. If G is any group, so what are the subgroups that are always there? The 0, right? The set consisting of just, the identity, sorry. Let's call the identity, right? The set consisting of just the identity, and at the other extreme, the whole group. Those are both subgroups. So, this guy has one element, and this guy has all the elements, okay? So, somehow this is not really answering my question, there's a lot in between. And I should say, actually, if these are the only subgroups, you guys proved that it has to be a cyclic group of order P. So there's usually going to be other subgroups than this. These are sort of, you always get these, but usually you have more. If you don't have more, you're actually, you're cyclic of order prime. Remember that stuff? So let me actually motivate that question with an example, and then we'll get to some of the technical stuff. So remember on your exam, well, so I'm going to say, what about the others? What about other subgroups? So again, let me just say that in words. That was a nice thing that you guys proved. If there are no other subgroups, then you can conclude that the group is a cyclic group of order P, right? That was a kind of nice thing that you can, somehow the structure of the subgroups tells you about the group itself. We'll see more of that flavor here. So let me give you an example from exam 1, the subgroups of Z10. Okay, now be careful, I'm doing Z10 plus, right? So back to the additive group, Z10. Well, remember Z10, so let's go through the analysis. Z10 is cyclic, all right? So we know Z10 is cyclic. Now, as an additive group, it's generated by 1. Actually, it's also on your homework, you know all the other generators, right? Anything relatively prime to 10 generates. So that was on your homework, right? So generated by, we can actually write it all down. We can write down all the generators, generated by 1, or what else is relatively prime to 10? I think 3 is, 7 is, 9 is, and that's it, right? So you can pick any of these and it'll be a generator. Any other guy won't generate, right? You proved that. Okay, so it's cyclic. What do you know about the subgroups of a cyclic group? We proved this. They're cyclic. So we proved that any subgroup of Z10 is also cyclic. So we actually know what they are, right? So again, I'm trying to put all the pieces together, all this stuff that we know about groups. This is kind of the flavor of the class now. We have these kind of richer and richer theory that we can now apply to something that you give me. You give me Z10, I can say, okay, it's cyclic, I can tell you what the generators are, I know that the subgroups are all cyclic, so we can actually write them all down, right? So the subgroups are, well, we've already done this, right? But I just want to, I want to look at some special property of the subgroups today. Okay, so of course you can generate by 0, you get the 0. We knew that. You can generate by 1, you get everything. You can generate by 2, and you get what? 2, 4, 6, 8, 0. Now this is additive, right? So hope that's not confusing, right? We were talking about multiplication before, and now it's addition. And the other one was generated by 5, right? So that has 5 and 0 in there. Well, so remember back to our question here. How many elements are in these subgroups? Well, so how many elements does this guy have? 1 element. How many does this have? 10 elements. How many does this have? 5. How many does this have? 2. Now G itself had 10 elements. And can you notice something about all these numbers? They all, what's that? They all they divide 10. Okay? So every subgroup I wrote down has a number of elements that divides the number of elements of the group. That's called Lagrange's theorem. We're going to maybe not finish the proof today, but that's going to be a general thing, that no matter any subgroup you find, any subgroup that's out there for any group, has order, has a number of elements that divides. Okay, so I won't write that down yet because we're shooting for that. We're going to have to go through some definitions first. But this is the kind of thing we want to know. You know, so you'd see this example and you'd wonder, if you were Lagrange at least, you would say, you know, is this actually always the case, that all subgroups have order that is a divisor of the size of the group? Okay, so we're going to get there eventually. But that's supposed to motivate, we're going to have, like I said, go through some technical stuff now in this coset business. So, let's just throw up the definition and work with it. So back to chapter 13, for real now, definition. This is how he starts. Actually, he starts chapter 13 with a little sort of philosophical aside about kind of what's a nice theorem or something like that. Or, yeah, so that was my philosophical aside of sort of what the nice theorem is going to look like. He actually doesn't give away the punchline until later. So let's do a definition here. So we're talking about subgroups. So let's let G be a group and let H be a subgroup. Okay, so again, the picture I have in mind is here's the big group G. H is a subgroup, right? H is the subset. And what do we know about H? It's a subgroup, so it's got the identity in it, right? So if you took the whole group, it's got, part of it is H. Could be the whole thing, could be just the identity, but it's... Okay, so that's our setup. Now, for an element A in the group, we define two things. So this notation, AH. So this is going to be, by definition, the set of things of the form A star H, so I'll just write AH, where H is in the subgroup. Okay, so we'll play around with this definition. So this is notation that says, take that element A and multiply it by everything in H. Remember, H is a subgroup, so it has many things maybe. And what you can do is for every element in the subgroup, hit it on the left by A. That cooks up a whole collection of things. This is called the left coset. Called A left coset. How does he call it? Well, it's called A left coset of H in G. And you can imagine what the other thing you can do is you can write HA, and that's going to be all the stuff you get by taking H times A, little h times A, for H in the subgroup. This is called, so maybe you can guess it, it's called the right coset. Called the right coset of H. Left coset, right coset. We'll do an example, I think, right now. He doesn't actually do an example until later, but he does. So now it sort of depends on the flavor of the taste of the author, but some books emphasize kind of left cosets, some emphasize right cosets. So I'm following Pinter here. I'm going to usually talk about right cosets, and we'll see what the relation is eventually. But we're usually going to talk about where, what we call right cosets, so these things. So usually focus on so let's do a couple examples, actually. I think this is hard to digest if you haven't seen it before. Actually, we can do this example. It wasn't one that I had in mind, but so if we were in the group G equals Z10, okay, let's take H to be, well, one of these will be the interesting. So let's take H to be this guy, the subgroup generate 5. So this is just 0 and 5, right? Okay, so let's just back up for a second. A coset, the data of a coset is a group, well, with a subgroup, and then you pick an element of the group and you do something, right? That's somehow the procedure. So let's ask, what are the cosets of H in G? Okay, so you guys with me? Z10 is the group, it has 10 elements. There's a subgroup consisting of just 0 and 5 in there, and I want to know what the cosets are. The right cosets. Okay, well, to make a coset, you have to take, we're doing this one, right coset, you have to take an element. So to build up cosets, you pick an element of the group, and you play this game, right? So, I don't know, what's your favorite element of G? Someone give me an element of G.
3.
3, okay. We'll do others. So let's pick an element of G. Right? Say 3 is in Z10. And you consider this thing, right? So in this case, well, it's H, which is, 5, and then the operation is star. Well, what is the operation here? We're in plus, so it's going to be plus the element A. So you guys see this notation? So it's the subgroup, operation, the element. So by definition, this is all the stuff you get by taking H plus 3, where H is in the subgroup 5. Oh, sorry, so I'm doing this is right? So the right subgroup, the right coset. Okay? So is this clear? I'm just unraveling the definition. So what is this thing? Well, how many elements are there what are the elements of H? It's just 0 and 5. Okay, so what does this set consist of? I can take 0 plus 3, or I can take 5 plus 3. Okay, well, what is that? That's 0 and 8. That's the coset.
3 and 8.
Thank you. All right, so good, that's not me. So 3 and 8, that's the coset. So 3, 8 is the coset, okay? That's the answer for one of the cosets. So someone else said take H to be 0. Okay, so that's one coset of H. Now let's say, take A to be, what do we say, 0 in Z10. The associated coset, the right coset, is given by, right? You take the subgroup and you add that element. And the notation is, right, you take all of the elements in there plus 0, where H is in 5, what is it in this case? If I take an element and I add 0 to it, I don't get anything new, right? So I'm just going to take this element, add 0, this element, add 0. So what do you get? 0 and 5. In fact, that's H. So actually, one of your cosets of H is H itself. All right, so this is a right coset of H, but it's actually equal to H, which is fine. In fact, that will always happen. There will always be one coset that equals H. You guys with me? So let's do one more, and then you're kind of getting a feel for what these guys look like. So what about if A equals 8? So the right coset is given by, let's see, what do? I take the subgroup plus the element, right? In general, it's subgroup operation element, okay? And again, this is the set of all H plus 8, where H is in the subgroup. Well, if I take this guy plus 8, what do I get? 8. And if I take this guy plus 8, I get 3. Well, that looks familiar. That's the same coset as this guy. So we took different A's, right? We took different elements of the group, and we got the same coset. So this is equal to the coset we wrote over there, which was 5 plus 3. So this is important. There's more than one way. In general, there's an infinite number of ways, not in this case, but more than one way of describing the same coset. So if I ask you what are the distinct cosets, what are the different ones you get, can you guys see what this is doing? So let's see if we can answer this. The distinct cosets of 5 in Z10 are, let's be a little bit more systematic. So I can take the guy plus 0. That consists of, I just erased it, right? That consisted of 0 and 5. I can take 5 plus 1. What does that consist of? Okay, is it clear what we're doing? Right, you take your subgroup and you just hit it with this element. And hit it means, you know, whatever the operation is on the right side. So good, this is 1 and 6. Well, then I've got 5 plus 2, which is 2 and 7, right? So if you guys see this, what's going on here? Okay. It looks like there's 10 things to do, but you guys have already seen that that's not right, right? So let's do a couple more here. So what is this? 3 and 8. 5 plus 4 is, what is it? 4 and 9. Now what is 5 plus 5? The subgroup 5 plus 5. That's going to be the same as this guy. Right? Because if I take 5 plus 5, so be careful, subgroup generated by 5 plus 5, that means I take the subgroup elements and hit them with 5. So I get 5 and 0, which is the same set as this, right? I mean, as a set, it's the same thing. Cosets are sets. Okay, so, and you can, what's this the same as? This is the same as 5 plus 8, right? So there's only 5 distinct cosets. But a kind of nice thing you already should be seeing here is that the cosets are a nice partition of the group. Right? So the picture now that you maybe have in mind here is that here's Z10, right? So Z10 consists of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? This is Z10 in some sense. Maybe I could have put it into a circle or something, but these are the elements of Z10. You know, and as you add, you go off, you wrap around, right? The usual modular mod 10 thing. And the cosets have broken this guy up into even-sized pieces. Right? They are partitioned. There's no elements in common. So, this guy is 0 and 5. And then I actually brought colors. Let's see if these work. Right, I mean, you guys can see what's happening here. So this guy is what? 1 and 6. And now I'm going to run out of colors. We can use this guy. So this is the 2 and 7. And then need 2 more colors. Got 2 more colors. So this one here is, of course, 3 and 8. And then the last one is this guy here. Gives me the chills a little bit, so I'm not going to use that color. But you see what's happening is it's partitioned the group into cosets. Okay, so let's try to sort of make some of these observations more formal. I'll kind of prove one thing and then we'll take a break. Are you guys getting a feel of what cosets are? So we'll do some more interesting examples. This is kind of baby, I mean, Z10 is kind of a nice abelian cyclic group, so we'll do an example with the symmetric group either today or next time. But let me prove some general facts about these cosets that we're going to use. Okay, so again, the right coset, right, HA is by definition the set of all things H times A where H is an H. Okay, so again, G is a group, H is a subgroup, and A is in G. Okay? So I want to prove a couple of general kind of lemmas. First thing is, well, lemma. If you have something that's in the coset HB, then if you take the coset HA, it actually equals HB. Okay, so what we're saying here is if you go back to this picture here, so you see that there's a coset, 5 plus 3, and I picked an element 8 in there. What we're saying is that if you take the coset associated 8, it's the same as the one you had. So somehow there's a nice relationship about taking an element of the coset, building a new one. It actually is not new. It's actually the same as that's what this is saying here. So let's prove this guy. I want to show that this set is equal to this set, right? So let's how do I pick an element of this guy, right? I have to say HA is an element of HA for some, right? If I want to take an element of this set, by definition it has to form little h times little a. Well, now since A is an element of HB, right? That's what we assume here. We know we have that I can write A as what? Since A is in this thing, so what does A equal? Okay, great. So maybe H1 times B. For H1. Does that make sense? So to say that you're in this set, by definition, means that you're something in H times B. So let's call that H1 times B. Okay? So, put that together. So HA is equal to H times H1B, which is equal to, so I'm just putting this together. I'm taking the A, how I know A looks, and I'm putting it here. So this is actually H times H1 times B, and look at that. It's something in H times B. So that implies that HA is actually an element of, it can be, HA can be written as something in H times B. So where does this live? The coset HB. You guys with me? So we took something in HA and we showed that it's in HB. So what does this imply? That this set HA is contained in HB. Right? What about the reverse direction? Okay, well, now we want to take an element in HB and show that it actually lives in HA. All right, so now for the reverse direction, the reverse inclusion, let's let, I don't know, let's let, I don't want to call it A, let's call it X be an element of HB, so that X is equal to, I don't know, H2, let's call it B, for some H2 in H. Are you guys comfortable with this, getting used to this notation, right? Big HB is all the set of all guys of the form little h times b for some little h in H, right? It's a weird notation, but we're going to use it a lot. So, okay, so X is H2B. Now, we know that HA was, we knew that this, we knew that A was in HB, right? That was our assumption. So again, we'll say that since A is in HB, we have, what do we say? A equals H1B. So in other words, B is equal to, what is that? H1 inverse A. I mean, just by multiplying by H1 inverse on the left. And now what can we do? Now let's put these two things together. So this implies that X is, what is it? H2 times H1 inverse A. Right? I mean, just plug and chug. Is that what it's called? H1 inverse A. But that's H2, H1 inverse A. This is two things in H being multiplied together. And remember, I'm using the fact that H is a subgroup, so that H1 inverse is in H. Right? This is why you need subgroups to be closed under, inverses and to be closed under multiplication. This is an element in H. Right, remember, if you take two elements in H, if you invert one, you're still in H. If you multiply them, you're still in H. That's the whole point of these subgroups. So therefore, X is an element of HA. Well, we took it to be an element of HB, and we show that it actually lives in HA. This implies that HB is a subgroup, a subset, of HA. And then, with the other inclusion there, we conclude that they're actually the same. Okay, so we're going to use that. Let's break now. So questions about kind of technical thing, but this is going to be useful.